Lesson 2.5, Continuity. A basic definition, which you might have heard in your past, is that you can trace the graph without lifting your pencil. If you see this graph right here, I can trace on this graph and be able to trace it without having to lift my pencil. From a calculus perspective, in order for a graph to have continuity, then there are three things that need to happen. I'm going to pick a point here, and I'm going to call it C. The first thing that has to happen is that f of c is defined. I definitely have a point on the graph. Part 2 is about the approach, and that's using limits. So I'm going to say the limit as x approaches c on the graph of f of x exists. If I look here at c, I have an approach to the same height of about a half. Part 3 puts the two together. The limit as we approach c on f of x is equal to the value at c. If the approaching height is the same as the defined height, you have continuity at a point. And you could analyze all the points on the function, because continuity is defined by the points. You can also have continuity at an end point. So the graph ends here at 3, 0 and is continuous on the way to 3, 0 and at 3, 0. How to define continuity at an end point? If we have a left end point, then we're going to say the limit as x approaches a. If I'm on the left, that means the approach is coming from the right, on f of x is equal to the value at a. So this value at -5 would be like the a value. This is the left continuity. The right-hand continuity would be over here at like 3, 0. So I would say the limit as x approaches, we'll use b this time, coming from the left to get to that right endpoint of f of x equals f at b. So this is right continuity. Well, if a function is not continuous, what could be happening? 3 different types that we're going to look at this year. Removable is a hole in the graph where if I fill in the hole, it makes the function continuous. Because we will have different types of holes in the graph, as we have in a jump discontinuity. So the ones that are removable is where you have a hole, and if you fill the hole in, it makes the function continuous. The infinite discontinuities is your vertical asymptotes. And the jump discontinuity is a break at a point where the function approaches 2 different heights. For the given x. Graphically, in this example right here, we have different types of discontinuities. We're going to move left to right and identify the different types of discontinuity. The first discontinuity is right here. I am looking and I see it's going off to infinity on the right, negative infinity on the left. So at x equaling -3, I have an infinite discontinuity. And that's the only type that's infinite because that's the only one that has an approach to negative infinity or positive infinity. X equaling -1 is a break in the graph, And look at, we have two different approaching heights. That's a jump discontinuity. And then I keep moving on, and I get to 4, a height here of -3, a height here of 4. So x equaling 4 is also a jump discontinuity. The next break in the graph occurs here at 8. This is a hole, but the approach to the hole is the same. And if I filled that in, if I moved this point down here and filled it in, it would make it continuous. So x equals 8 is removable. Determining continuity from functions. What you do is you look at the pieces of the function themselves. Make sure we're not dividing, because if you divide, then you have breaks in the graph for either vertical asymptotes or horizontal. This one has no breaks in the graph. So what I'm concerned then is what's going on at -1. Do I have a break with different heights, which would be a jump discontinuity? So we're going to analyze using limits each piece. First piece is less than -1, so I'm going to say -1 coming from the left on my function g. If I analyze that piece, it's -1 squared, which gives me a -1. Then I go to the other side. The limit as x approaches -1 from the right on g. That would be 4 times -1 plus 3, which gives me -1. This function is continuous everywhere because the two pieces are coming together and equal to at less than or equal to -1. So they come together and are defined. I am continuous from -infinity to infinity, or all reals. For this function, no fractions, so I'm going to look at what's going on at how it's defined at -4. Looks like I have defined point at -4, 6. The question is, does this defined point exist on this graph? Or is it somewhere else, like up here? So I'm going to look at the limit as x approaches -4, and I'm saying both sides here because this means not at -4, but everywhere else. For h of x, that's going to be 3/4 times -4 plus 8. That's going to give me a -3 plus 8, which gives me 5. So the approaching height is a height of 5, but the actual point is at 6. That means we have a break in the graph at that -4. So I'm going to say it is continuous from -infinity to -4, joined with -4 to positive infinity. So this indicates a break at -4. Or you could say the set of all reals such that x does not equal -4. In calculus, we tend to use interval notation, not set notation. Here's another graph. We're going to find all values of c such that the specified function has a discontinuity at that c. And then for each one, we're determining which conditions of the definition of continuity fail to be satisfied. That was on the front page. The front page says f of c is defined as part 1. The limit exists as part 2. And the limit equals the point. Let's find our first discontinuity. Here we have a break at -6. So I'm going to say x equals -6 is my first such c. And for this one, I go through the definition. Does it exist at -6? It does. It's defined right here. So it passes that part. Part 2 says the limit exists. Well, that means the approaching height is the same. And this one does not. So we're going to say the limit as x approaches -6 on function f of x does not exist. So that's violating part 2 of the definition of continuity. My next break, I'm looking here at -3. I've got this vertical asymptote, which means I'm approaching unbounded going down and approaching unbounded going up. So x equaling -3 is a discontinuity. Where does it fail? Let's start with part 1. Part 1 says that it has to be defined. I have nowhere where it's defined. So I'm going to say f at -3 is undefined. My next one is at 0. X equals 0 is a break in the graph. And for this one, we're going to say that the limit values are not existing. They're individually existing, but not at 0. So the limit as x approaches 0 on f of x is equal to does not exist. X equaling 3, I look there, it is defined there, but the approaching heights are different. So we're failing the limit as x approaches 3 of f of x is equal to dne. I'm going to add in another one because I want to illustrate what happens when you have a removable discontinuity. So I'm going to put an open circle here. Please add that to your graph. And then put a point up here at 5, 1. I would say then that I have another discontinuity at x equaling 5. And it is defined here at 5, 1. My limit is approaching the same height, so step 2 is okay. But the removable discontinuities fail step 3. The limit as you approach 5 on f of x doesn't equal the function's value at 5. In this one below, we're going to check and circle for where the function is continuous. -infinity to -2. That's going up and approaching this asymptote. Well, it doesn't say closed here, and if I keep reading the graph, it goes infinitely down. That is considered continuous because I don't have to worry about -2. This case, I do have to worry about -2, and it is defined at -2 right here. But the problem is I am coming from the left, from -infinity. So when I go from -infinity, I am looking to be connected to a specific height at -2. And this is not coming from the left connected to a particular height. So this is considered to be not continuous. Then I go -2 to 0. That means the region, not including this, but in between the -2 and 0. That is continuous. -2, don't include -2, but definitely include 0. Well, if I look here at 0, the curve crosses at 0, 0. It is defined there, and it's connected to that 0, 0. That is considered to be continuous. -2, now it's included to 0. But this region means from the right of -2 all the way to 0. There is connectedness starting at -2 all the way to 0. This path is connected and defined. That is considered continuous. 1 to 2, open. Here is 1, here is 2. Open circles here, but I am not including 1 and 2. I'm analyzing between, which is continuous. 1 to 2, including the endpoints, is not continuous because I am not defined at 1 and I'm not defined at 2 in relation to the curve. I am defined at 1 and 2, but not connected to the curve. And then from 2 to 5, if I look 2 to 5, here's 2, and going to the right, 5, the problem is right here at 2. I would need to have that closed circle up here to be continuous from 2 to 5. You have to have connectedness to the path and defined. So this one is not continuous. I would take a moment, pause the video, and try the next 3 graphs and then restart it to see how it works. We're graphing f, where it's continuous everywhere, except at x equals 4, so something's going on at 4 with somebody, at which point it is continuous from the left. So to be continuous, I have to have a defined point. So I'm going to put a point anywhere on 4 somebody. To be continuous from the left, this is left of 4. So I have to draw something so that I'm going to be connecting to my defined point and keep going in this direction. This is giving me continuity from the left, and then I have to be continuous everywhere except the 4. So that means I want to jump from here to another value and create another piece. So I definitely have continuity everywhere but 4, and now we're continuous from the left. Two-sided limit at 1, but not continuous. So I go to 1, pick a point anywhere you want, and then I want to be not continuous at 1. Okay, well, I just gave myself a point, and if I have to be not continuous at 1, then I want it to have a two-sided limit as well. I'm going to do another circle that's open and say I'm going to connect to this open circle in any way, shape that you would like, so that I have what's called a two-sided limit, but I put my defined point up here, so I am not continuous at 1. You could also have a graph that would have an open circle at 1 somebody, and just make sure you are connected to your point, and you don't necessarily have to have the defined value. It would still be not continuous. F is not continuous at x equals 0, but if its value at x equals 0 is changed from 0, negative 2 to f of 0 equals 1, it becomes continuous. I have 2 things going on right now at 0. I have 0, 1, and they talk about 0, negative 2. I'm going to start, because it's 2 different points that they're referring to, with both of them being open circles. Then I'm going to read it again. If you're changing it from here and moving it to 0, it becomes continuous. In order for it to be continuous means at 0, 1, I have to have some kind of connected path in my graph. So that means I'm showing the connectedness at 1. Now to become continuous, if I take what is happening at 0, negative 2 and put it here, that means this 0, negative 2 has to be closed in, because it's talking about moving it to make the function continuous. Algebraically, points of discontinuity. When you look at a function, use your pre-calc skills to identify any points of discontinuity. My first one is a polynomial function. They don't have any points of discontinuity. 13 is a rational function, and if you remember from last year, we cannot have division by 0. So I'm going to say x minus 4 equals 0, because I am looking specifically for the values at which it is not continuous. So I'm saying these values, this is where it's not. So x equals 4 is a point where the graph is not continuous. Then it asks to identify its removable. Because this is a factor in the denominator only, it's a vertical asymptote, which is an infinite discontinuity. In 14, it is more helpful when you have higher degree polynomials to rewrite them using your factoring skills, and then you can identify those discontinuities a little bit easier. I notice I have a common factor here at x equaling negative 7. So I'm going to say x equals negative 7 is a point of discontinuity in the graph. And what's going on, because it's a common factor, this one is removable. And then when I look at 7, it makes 0 in the bottom, so x equals 7 is a discontinuity. And because it makes 0 in the denominator only, this one is an infinite discontinuity. Absolute value of x squared minus 4, I'm taking a quadratic and I'm reflecting to make it all positive. Reflecting it does not chop the graph. If you think to your x squared minus 4 visually, here's what we have. To make it an absolute value, I am taking and reflecting this piece up, like this. So once I reflect it, I still have a continuous graph. So this is none. Reflecting is not breaking it apart. 16, higher degree polynomial, so I'm going to do a rewrite. And I take a look, my common factor is x. So I'm going to say if x equals 0, that's a discontinuity. Because it exists in the numerator and the denominator, that's the removable type. I have another discontinuity at x equals -2 because it's making the denominator 0. That one, because it's denominator only, is what we call an infinite discontinuity. 17, do some more factoring. X plus 1, x minus 1 over x minus 1. The only thing that's making a 0 is the value of 1. So I'm going to say x equals 1 is a discontinuity. The type is removable because it's that common factor. X squared plus 49 is different than x squared minus 49. If you have x squared plus 9, and I solve to equaling 0, I get x squared equals -9, and I can't take the square root of a negative number. This graph does not have any discontinuities. Absolute value of x minus 8. Here the absolute value matters because it's part of the denominator. So I'm setting the denominator equal to 0. Absolute value of x is equal to 8. And I come up with x equaling plus or minus 8. Both of these values make it 0 in the denominator only. So these are the infinite type of discontinuity. Finding a value for the constant k that's going to make this function continuous. Each piece alone, quadratic, linear, would be continuous. The question is, to make it continuous, I have to look at this breaking point where they're both defined, which is potentially at -3. If I want to make it continuous, I want the approach to be the same. So I'm going to say that my kx squared height has to equal the height of the function. Now, where do they have to be equal? They have to be equal where it's defined at -3. So I'm going to say -3 squared is a 9. This becomes 9k. -3 times 4 is -12 plus 3. I'm going to get 9k equaling -9. The value of k that makes this function continuous is -1. The last part, we know information about f and g, that they are continuous. And if they're continuous, we also know that f of -1 equals -5, and then I have this limit statement right here. Remember, by continuity, defined values are equal to limit values. So when I'm looking up here, I'm going to use my difference rule with my limit and say that the limit as x approaches -1 of f of x minus 2 times, that's the constant multiple rule, the limit as x approaches -1 of g of x should equal 11. Well, f at -1 is -5. Because we're continuous, the point value should equal the limit value. So I'm going to say now -5 minus 2 times the limit as x approaches negative 1 of g of x is equal to 11. We're solving now to get this limit value, because in part B I want the limit value, and in part A I want the point value. Because they're continuous, they should be the same. So I'm going to say negative 2, limit x approaches negative 1 of g of x is equal to a positive 16 when I add the 5 over. Last step is to divide by that negative 2 to get a value of negative 8. So the limit value is negative 8 and the point value is negative 8 because of the definition of continuity.